Good day, friends, and welcome to today's WASE online channel. I'm Philip, your instructor. But before we start our lesson for today, I need you to subscribe for our channel if you've not already done that. We need your subscription for the survival of this program. To do this, just go below this video and tap the subscribe button. Thank you so much for doing this for us. Now let's look at our activities for today. So we are continuing with set and set operations. Today under set and set operations, we'll be looking at part 2. And in this part, we'll be looking at the following. First, we'll be looking at subsets. Then we will look at operations on sets. I believe we can start our activity for today. So let's start now. Let's start with subsets. To better appreciate subsets, let's use the following example. Let's take the set A. This is the set A. It contains the elements 1, 2, 3, 4, 5, 6, 7, 8, and 9. Now let's take another set. Set B. Its members are 1, 2, and 3. Now, what can you say about the two sets A and B? Well, you realize that all the members of set B, 1, 2, 3, can be found in set A. What this means is that the whole of set B is in set A. So we say that set B is a subset of set A, or B is a subset of A. Now let's use a diagram to represent this. So we have our set A. Its members are 1, 2, 3, 4, 5, 6, 7, 8, and 9. Now let's get the members of set B. These are the members of set B. They are 1, 2, and 3. As the diagram depicts, the set B is in the set A. So set B is a subset of the set A. So a subset is a set whose members can be found in a bigger set. The bigger set is called a superset. So let's look at some examples. We have our set A with its members 1 to 9. We have set B with its members 1, 3, and 4. Since all the members of set B can be found in set A, we can say that B is a subset of A. Let's take the set C with the members or elements 6, 7, and 8. All of these members 6, 7, and 8 can be found in the set A. So C is also a subset of A. Let's take the set D with its members 0, 1, and 2. The set D does not have all of its members in set A. As you can see, 0, which is a member of set D, cannot be found in set A. So, D is not a subset of A. Now, let's look at the set E with the elements or members A, B, and C. As you can see, set E is completely off. None of its members can be found in set A. So, E is also not a subset of A. With these examples, let's repeat the definition of a subset. So, a subset is a set whose members can be found in a bigger set called a superset. Now, under subsets, let's look at the following symbols. This is the first symbol. It means it's a subset of. Let's look at how we can use this symbol. Example, we have B is a subset of A. Now, this sentence is a subset of can be replaced by its symbol. So, B is a subset of A can be written this way. We have the B, then the subset symbol, followed by A, which will be read as B is a subset of A. Let's look at another symbol. This symbol means it's not a subset of. As you can see, the not a subset of symbol is actually a subset of symbol that has been cancelled. Let's use it in an example. In this example, we have the statement E is not a subset of A. So, we would replace the statement is not a subset of with its symbol. When we do this, we will get E followed by the not a subset of symbol, then A, which would also be read as E is not a subset of A. Now, at this point, we know what subsets are. We also know the symbol used to represent subset of, and we also know the symbol used to represent not a subset of. Now, but assuming you are given a set and you are asked to list all the subsets of the set, what would you do? That is what we'll be learning at this point. So, we'll be learning to list all the subsets of a set. Let's take the set X with its members A and B. We want to list all the subsets of the set X. This is the first subset of the set X. That is A in curly brackets. Remember that because subsets are sets, they should always be in curly brackets. Without the curly brackets, you are wrong. So, this is not a subset of the set X. Rather, A in curly brackets is a subset of the set X. Let's look at another subset of the set X. This is another subset of the set X. That is B in curly brackets. Remember, you can't write B because B is just a member of X. But the subset name is B in curly brackets. So, these are the two main subsets of the set X. But I'll need us to remember that we are not done yet. Anytime you are asked to list all the subsets of a set, after you have finished listing your main subsets, always remember to add the set itself and an empty set to that list. So, this is the set itself. It should be added to the list. And this is an empty set. It should also be added to the list. So, these are the subsets of the set X. They are A in curly brackets, B in curly brackets, the set itself, and an empty set. They are 4 in number. So, the number of subsets of X is equals to 4. As simple as that. Now, is it possible for us to tell the number of subsets of the set X without necessarily listing these subsets? Yes, it is very possible. Let's look at how we can do this. To do this, we would follow this general rule. Number of subsets equals to 2 exponent n, where n is the cardinality of the set. I believe you've not forgotten the term cardinality of sets. It appeared in our first video on sets and set operations. For those who have forgotten, the cardinality of a set is the number of members of that set, or the number of elements in that set. So, for example, for this set X, its cardinality is 2 because it has 2 members or 2 elements in it. So, for this set, n is equals to 2. Remember, we said n is the cardinality of the set. Therefore, we will substitute n equals to 2 into the equation above. And that will give us number of subsets equals to 2 exponent 2. 2 exponent 2 is 2 times 2, which is 4. So, number of subsets equals to 4. So, as you've realized, without listing all the subsets of the set X, we've been able to tell how many subsets X has by following this general rule. And I'll need you to remember this. Let's look at another example. We will list all the subsets of the set B. Set B has the members or elements 1, 2, and 3. Let's list its subsets. So we first have 1 in curly brackets. We then have 2 in curly brackets. Then 3 in curly brackets. We also have 1, 2 in curly bracket, then 1 tray in curly bracket, then 2 tray in curly bracket. We now have the set itself. Then finally we have an empty set. Very easy, isn't it? So in all, set B has 8 subsets. Now let's use our general rule to calculate the number of subsets of set B. So let's first state the general rule. Number of subsets equals to 2 exponent n, where n is the cardinality of the set. In this case, the cardinality of the set B is 3 because B has 3 members or elements. So n is equals to 3. We will substitute n equals to 3 into the above equation and we will get number of subsets equals to 2 exponent 3. 2 exponent 3 is 2 times 2 times 2. That is 8. So number of subsets equals to 8. As you can see, without listing all the subsets of the set B, we've been able to use the general rule above to tell how many subsets the set B has. And please, I'll need you to keep this general rule. It is very important. At this point, we'll be looking at operations on sets. We will first look at intersection of sets. Let's remember that we use this symbol to represent intersection of sets. We will then look at union of sets. Let's note that we use this symbol to represent union of sets. We will then look at complement of sets. This is the symbol used to represent complement of sets. It is the apostrophe sign. Still under complement of sets, let's note that complement of B or B complement will be written as this. So we have the B followed by the apostrophe sign. Please, I'll need you to remember these symbols. They are very important. In fact, we'll need them in our next lessons. Let's start by looking at intersection of sets. We would use the following examples to explain this concept of intersection. So first, let's take the set A with the members or elements 1, 2, and 3. Let's take another set B with the members 2, 3, 4, and 5. Now, we'll be looking for A intersection B. This is how we write A intersection B. We first write A, followed by the intersection sign, then B. Now, how do we find A intersection B. To do this, you need to look at the two sets A and B and identify items that can be found in both of them at the same time. You realize that the number 2 can be found in set A and it can also be found in set B. So we pick it. You also realize that the number 3 can be found in set A and can also be found in set B. So we pick that one as well. So the two numbers or members 2 and 3 can be found in both set A and in set B. Therefore, the intersection of A and B will be the numbers 2 and 3. But of course, you must remember to always put them in a curly bracket as shown on the screen. We can use a diagram to illustrate this. So we have the set A with its members 1, 2 and 3. And we also have our set B with its members 2, 3, 4 and 5. And as you can see from the diagram, 2 and 3 is common to the two sets. So they interlocked as shown on the screen. Now, let's add the set C. Set C has the members 5, 6, 7, 8 and 9. Now, let's find B intersection C. This is our B intersection C. So we have B followed by our intersection sign, then C. Now, how do we find B intersection C? So we go to the two sets, set B and set C, and we look for members or elements that can be found in the two of them at the same time. When we do this, you'd realize that the element 5 can be found in set B and it can also be found in set C at the same time. It is the only element in B and C at the same time. So that is the answer. So B intersection C is equals to 5 in curly bracket. Remember, just writing 5 without the curly bracket gives you a wrong answer. So write your curly bracket, show it. Again, let's illustrate this with a diagram. So we have our set B with its members 2, 3, 4 and 5. And we have our set C with its members 5, 6, 7, 8 and 9. As you can see, 5 is common to both sets, so it is the point of intersection. Let's look at the last example under intersection. Let's look for A intersection C. So, as usual, we will go to the set A and the set C, and we will look for elements or members that can be found in both of them at the same time. Is there anything like that? When you go to set A, the elements are 1, 2 and 3. When you go to set C, the elements are 5, 6, 7, 8 and 9. Here, you realize that the two sets do not have anything in common. So what it means is that they do not have an intersection. What this means is that their intersection would be empty. So we would use the empty set or the null set to represent A intersection B. So our answer is this empty set. Let's use a diagram to illustrate this. So we have our set A with its members 1, 2, and 3. And we also have our set C with its members 5, 6, 7, 8, and 9. But of course, because they do not have anything in common, they form a disjoint set. We'll look at a disjoint set in our next slide. So let's look at a disjoint set. Let's remember that two sets are said to be disjoint if they do not intersect. Let's explain this with an example. So we have the set B with its members A, B, C, and D. We also have the set C with its members M, N, O, P, and Q. Now, because these two sets do not have anything in common, their intersection would be empty. So we represent it with the null set. So our B intersection C is equals to a null set or an empty set. Let's illustrate this with a diagram. Let's remember that diagrams that are used to represent sets are called Venn diagrams. We'll look at this in details in part 3 of sets and set operations. So we have our set B with its members A, B, C, and D. We also have our set C with its members M, N, O, P, and Q. And of course, because they do not have anything in common, they form a disjoint set. So as you can see, the two Venn diagrams representing set B and set C were not intersected. Now let's look at union of sets. The term union comes from the word to unite. When you have two cards uniting with three cards, what it means is that you join them together to form 5 cards. So we are going to apply the same idea to explain the term union of sets. To get the union of two sets, we have to put the members of the two sets together without doing double counting. Later, we would understand what it means by we shouldn't do double counting. So let's use some examples to explain the term or concept union of sets. Let's take the set A with its members 1, 2, and 3. Let's also take the set B with its members 2, 3, 4, 5. Let's look for A union B. So this is how you write A union B. You first write A followed by the union symbol then B. At this point, how do we find A union B? To do this, we would just simply have to join the members of set A to the members of set B. But once we do that, items that appear twice are not double counted. When we join the members of A and B together, we will get 1, 2, 3, 4, and 5. Remember, 2 and 3 appeared in A and in B. So we did not double count them. We only wrote them once. So although we have 2 in A and 2 in B, we wrote only 1, 2. And although we have 3 in A and 3 in B, we wrote only 1, 3. So that is how we do union. So our answer will be equals to 1, 2, 3, 4, and 5, all in curly brackets. Remember, without the curly brackets, you are wrong. So always bring the curly brackets. Let's illustrate this with the diagram. Of course, a Venn diagram. So we have the set A with its members 1, 2, and 3. And we have the set B with its members 2, 3, 4, and 5. Union means to join the two sets together. So let's quickly do that. So that is the union of the two sets A and B. And as you can see from the diagram, the 2 and the 3, although they appeared in both sets, they are not repeated. So we have 1, 2, 3, 4, and 5. As simple as that. Now let's add the set C with its members 5, 6, 7, 8, and 9. Let's find A union C. To do this, you just take the members or element of the set A and the members of the set C and join them together. When we do this, our answer will be this: 1, 2, 3, 5, 6, 7, 8, and 9, all in curly brackets. Let's illustrate this with the diagram. So we have our set A with its members 1, 2, and 3. And we have our set C with its members 5, 6, 7, 8, and 9. The two sets are separated because they do not have anything in common. In other words, they are disjoint. When we join them to form a union, we will get something like this. As you can see, the two sets are still separated, but we've shaded them with the same color to show that they are joined together to form a union. Now, I'll need us to note the following about the union of sets. First, you can be asked to find the union of two sets that intersect. We've already looked at this type of union. Next, you can be asked to find the union of two sets that are disjoint. We've also already looked at this type of union. Finally, you can be asked to find the union of two sets, one of which is a subset of the other. So these are the various types of union of set questions you are likely going to encounter. For the subset type, we've not already looked at it, so let's look at it in our next slide. So let's look at the union of two sets, one of which is a subset of the other. In other words, we are looking for the union of a subset and its superset. So let's take the set A. The members of set A are 1, 2, and 3. Let's take the set C. The members of set C are 1, 2, 3, 4, 5, 6, 7, 8, and 9. Now, a closer look at the two sets A and C reveals that set A has all of its members in set C. So that makes set A a subset to the set C. Now, let's look for A union C. To find A union C, we must add all the members of set A to all the members of set C. When we join them together, we will get 1, 2, 3, 4, 5, 6, 7, 8, and 9, all in curly brackets. Now let's illustrate this with a diagram. So we have the set C with all of its members from 1 to 9. And we also have the set A with its members 1, 2, and 3. As we can see from the diagram, the set A has its members in the set C. So that makes set A a subset of the set C. Now, to get our union, we have to join the members of set A to the members of set C without doing double counting. Therefore, our region for A union C is this. This red region combines set A and set C to form a union. Now, what have you noticed about this union? Whenever you have a subset and a superset, and you are taking the union of the two sets, the answer is always the superset. For example, when we solve for A union C, answer was 1, 2, 3 to 9. You'd realize that this answer is the same as our set C, which is the superset. So, a subset union its superset is always the superset. Now, let's look at complement of sets. To do this, let's use the following examples. So let's take the set A. with its members 1, 2, and 3. Let's take the universal set. Its members are 1 to 9. I believe you've not forgotten the symbol for universal set. If you have, then please use this opportunity to remind yourself of this symbol. Now let's come back to complement of sets. We will be looking for a complement. Before we look for a complement, I'll need us to note that anytime we are to do the complement of a set, we always have to do this in relation to the universal set. So universal set is always important if we have to do the complement of a set. We are doing a complement, so we will compare the set A to the universal set. Now, a complement simply means that all the members in the universal set without the members of set A. So this is what we're going to do. We'll strike out all the elements of set A that appear in the universal set. We'll strike them out, and the members that would remain in the universal set will be the complement of A, or A complement. So let's quickly do this. The first element in set A is 1. So let's strike it out from the universal set. The second element in set A is 2. So let's strike this out from the universal set. The third element in set A is 3. So let's strike it out from the universal set. So what this means is that the elements left in the universal set are 4, 5, 6, 7, 8, and 9. A complement is therefore equals to 4, 5, 6, 7, 8, and 9, all in curly brackets. That's very easy, right? Let's look at another example. So with this example, we have set B with the members A, C, and F. And we have our universal set A, B, C, D, E, F, G, H, and I. Let's look for B complement. As we already know, B complement simply means all members in the universal set without the members of set B. So, as usual, we'll strike the members of set B from the universal set. The remaining members in the universal set will be our B complement. So let's quickly do this. The first member in set B is A. So let's strike A out from the universal set. The second member in set B is C. So let's strike C out from the universal set. The third element in set B is F. So let's strike F out from the universal set. So after striking out A, C, and F from the universal set, we are left with B, D, E, G, H, and I. Therefore, B complement will be equals to B, D, E, G, H, and I, all in curly brackets. Now, at this point, we know what complement of sets are, but I'll need us to use a diagram to explain this concept. So let's look at that quickly. So we have our set A and the universal set. And this is our A complement from the two sets. And I believe you know how we arrive at this A complement. Now, let's use a diagram to illustrate this concept of complement of sets. So first, we'll show our universal set with its members 1 to 9. We will then show our set A with its members 1, 2, and 3. As you can see from the diagram, set A is inside the universal set. So that tells us that sets are usually, in fact, all the time, subsets to their universal set. Now, we'll be shading A complement very soon. I remember we said that A complement is anything inside the universal set other than A. So what we are going to do is this: we are going to shade the entire region of the universal set, but we will not shade the region of A. So that's how we are going to do this. So we'll get something like this when we shade A complement. From the diagram, you'd realize that the numbers 1, 2, and 3 were not shaded, which means that they are not part of the A complement list. Those numbers that were shaded with red are 4, 5, 6, 7, 8, and 9. They are in the complement of A list. Still under complement, I'll need us to look at these special types of complements. In fact, you need to know them. So first, we'll look at the complement of an empty set. Then we'll look at the complement of a universal set. Then finally, we'll look at the complement of a set. The third one looks some way, but by the time you are done, you get what that means. But in all of these, I think the most important thing is for you to know how to do the complement of set. Once you know how to do the complement of set, these three special types of complement shouldn't be a problem. You just follow the same steps and you get them right. So let's look at them one after the other. So we'll start by looking first at the complement of an empty set. Here we have the empty set A and its universal set having members from 1, 2, 3 to 9. So here we are looking for the complement of the set A. And remember, the set A is an empty or null set. As usual, we will go into the universal set and look for elements of set A and we will cancel them out. But it seems here that there is nothing in set A you find in the universal set. The reason being that set A is empty, so there is nothing in it. So what it means is that there is nothing to cancel out from the universal set. So if there is nothing to cancel out, what it means is that the entire element of the universal set would have to be the answer. Therefore, A complement is equals to 1, 2, 3, 4, 5, 6, 7, 8, and 9, the same element in the universal set. Remember, they should all be in curly brackets. Therefore, we can say that the complement of an empty set is always equals to the universal set. Next, let's look at the complement of the universal set. So here we have a universal set with its content shown inside the curly brackets. And we also have the same universal set with the same content. Now we want to find the complement of the first universal set over the second universal set. So complement of the first universal set. So to do this, we would have to go to the universal set, the second universal set, and cancel out all the members in the second universal set that are also in the first universal set. So let's quickly do this. Now, because the first universal set has the same element as the second universal set, so what this means is that we would actually end up cancelling all the elements in the second universal set, like this. So now that we've cancelled out the content of the second universal set, what is left? Nothing. So if there is nothing, we have an empty set. So what this means is that the complement of a universal set should always be an empty set. Now let's look at the complement of a set. Wow, that looks very long and convoluted. Well, but it's also very easy to grasp this. What he's saying is this. You have the complement of a set and you are taking another complement of that set. So for example, you have a complement all into bracket, complement of that a complement. That's what this is saying. So let's use the following example to do this. Okay, so we have the set A and its universal set as shown on the screen. So first, this is our A complement. How did we do this? We just cancelled out the members of A from the universal set. And you got 4, 5, 6, 7, 8, and 9 as your A complement, right? So now let's find our A complement all into bracket complement. To do this, we need to compare our A complement with the universal set. So as usual, we will go into the universal set and we'll cancel out all the members of the universal set that appear in set A complement. A complement contains 4, so we'll cancel it out. It contains 5, so we'll cancel 5 out. 6, so we'll cancel 6 out. 7, so we'll cancel 7 out. 8, so we'll cancel 8 out. Then 9, so we'll cancel 9 out. So what are we left with in the universal set? We are left with 1, 2, and 3. Therefore, our A complement into bracket complement will be equals to 1, 2, 3, all in curly brackets. What would you say about this answer? 1, 2, 3, all in curly brackets. Well, you realize that 1, 2, 3, all in curly brackets is the same as A or set A. From this, we can say that the complement of a set is the same as the set. In this example, the complement of A is the same as set A. Well, friends, this brings us to the end of part 2 of set and set operations. You can now go to the next video, which is the part 3 of sets and set operations. And in part 3, we will be looking at properties of set operations. Thank you very much and stay safe. But remember, if you've not already subscribed for this channel, please move below this video and tap the subscription button. Thank you so much. Stay safe once again.